Hi everyone. Let's start with a question today. I would like to ask a question. How many of you run containers in production? Can you raise your hands if you run containers in production? And keep it raised if you ever have faced a security incident in the past. So today, hi everyone, and welcome you all to Open Source Summit India. And we are here. This is Akshat Khanna with my co-speaker Unnati. We are here to talk and share some of the great and new insights on container security. So our talk title, Zero Trust Containers, Rethinking the Security in Age of Ephemeral Workloads. So do you know that attackers tend to attack at your containers just within an hour of deployment? Yeah, that's true. So here we are to discuss how attackers do that and how we can prevent that. So in this, we'll see how zero trust containers principles basically change the story. Myself, Akshat Khanna. I am a certified Kubernetes administrator and an application developer. Work as SD2 at Angel One. Where we are scaling the trading platform to support millions of users.
Hi everyone, I'm Unnati Mishra. I work as a research and development engineer at VMware by Broadcom. At VMware, I work with the Kubernetes distribution team. I'm also a certified Kubernetes administrator and developer. And you can see me at various public conferences speaking and giving various talks. And apart from doing all the tech stuff, you can find me making YouTube videos and dancing. So let's jump in. This will be the agenda for today's session. First, we'll look at the modern container security crisis, that even after applying so much security on our containers, why breaches happen. For the interest of new people here, we'll go through the basics of containers and ephemeral workloads. We'll see why the traditional container security fails and how we can overcome them using the zero trust policy for containers. We'll look at some key open source tools for zero trust. We'll also be giving a demo on detecting and defending the containers, defending the container attacks. We'll be giving the real-world attack scenarios and the success stories. We'll end the session with the key takeaways.
Now let's understand what modern container security crisis is. So in modern container security, I'll start with a real-world scenario. So a financial services firm had their so-called green-lit containers that they done their security scanning and all things were green there. But when the things moved to the production, the things changed. And they had an attack which supported they had an attack with just within few minutes of their deployment. Yeah, that's true. In this past decade, in this current decade, what happened is the companies are rapidly adapting containers. So you can look at the numbers. There are 600 vulnerabilities in container images on an average. And it takes, as I told, less than 1 hour to detect and compromise new containers. 67% of the vulnerabilities are missed by these static scanning. And the 94% of the security teams are concerned about these container securities.
Let's see what are containers and ephemeral workloads. Containers are, they package your code, the dependencies, and everything that you need for your project in a simple portable unit. So nowadays, organizations are adopting containers at a very fast pace. But our security mechanisms are not at pace with the containers, with the level the organizations are adopting the containers. They are adopting the container mechanism because of the faster deployment cycle, resource efficiency, and microservices enablement. Let's see what are ephemeral workloads. So these are short-lived temporary workloads which come up for serving a purpose and then they disappear. You can think of it as a pop-up food stall that come outside the malls, they serve the purpose, and then they disappear. One more example, like you have Black Friday sale or Amazon Republic Day sale. So on that time, the e-commerce platforms scale their containers from 10,000 to 1 million to serve the customer traffic. So they come up for a reason to support the customer traffic or perform some specific task, and then they disappear. So these are the basic characteristics of the ephemeral workloads. That is, they terminate automatically, they scale based on demand, and then they spin up very quickly and disappear. This is very powerful, but we have a security nightmare here, because how do we protect something that is only existing for a few minutes or a second?
Now let's understand what's the core problem, why traditional security fails. So traditional security is like a busy airport with a castle-like boundaries that is for a world that no longer exists. So let's try to understand what are the limitations or what are the problems here. So static analysis, it's like checking the luggage of the passengers before they are going for the journey. But we never, in static analysis, we never checks what happens during the journey. So we miss the runtime behavior here. So the attackers are now the intelligent enough, and the static analysis is passed. But when things move to production, things changes, and the attackers have learned to like have malicious activities during the runtime. And second thing is parameter-based thinking. So what happens is, in older days, when the network, if you are inside the network, you were trusted. But there is nothing as in the container. So if you are inside the containers, there is nothing, like it is meaningless because the workloads are constantly moving and changing. Now, what are the core problems here? Why the traditional container security fails? So there is a shared kernel risk. Basically, what happens here is when a container is running on a host, there is an underlying Linux kernel. So if one of the container is compromised, the attackers can have access to complete system. In a one single breach, it's not just one application that is compromised, it's the complete system. Similarly, configuration drift. What happens is the build time state of the container, and when it goes through the production, it's entirely different. What happens is there might be some of the environment variables that are injected or configurations that are changed or any patch which is applied on the fly. So if these environment variables or configurations are compromised, there is a high risk of DB credentials or other secrets that might be compromised.
So now how we can overcome this traditional security threats? By using the zero trust policy for containers. So by default, we have this policy, never verify but trust the source. But now we have never trust, always verify policy. We are always verifying what goes inside the container, who is accessing the container, and what policies are changed inside the container. We give the cryptographic identity for each workload, and we attest them or we monitor them continuously so that breaches are limited. We have continuous verification, as I already told. For runtime monitoring and analysis of the containers continuously, we use some open source tools that we'll discuss further. This is the zero trust architecture diagram. We have 4 layers in it. So even if one layer is breached, the attacker has to cross other 3 layers. We have supply chain layer, identity layer, policy layer, and runtime layer. So in the supply chain layer, we sign the container images, we scan for vulnerabilities, and we generate a software bill of material, which tells us what goes inside our container and how to protect our containers if there's some vulnerability. In the identity layer, we provide cryptographic identities for each workload or container. And the open source tool, which is SPIFFE and SPIRE, we'll be discussing it further. They attest the workload continuously, or they monitor the changes continuously so that the breaches are limited.
Next up is the policy layer. Policy layer basically draws the boundary and set the rules. For example, we have Kubernetes admission controllers, which decides whether the workload even have the permission to run on the cluster or not. And we have AppArmor or SE Linux, which prevents the workloads for accessing any sensitive information on your cluster. And we have network policies as well, which will basically safeguard, or it will make sure all the communications which happens in the cluster or your environment are secure and with the peers only. Next up is the real-time layer. So Falco monitors all the anomalies in the real time. If there is any program calls or file operations or maybe network calls, Falco is monitoring that in real time. And if any anomalous behavior is detected, it will raise the alert instantly. And here's the magic. So as soon as the Falco raises the alert, we can have it even on Slack, or we can like integrate multiple webhooks or even emails. So what will happen here is we can even have policies based on our Falco monitoring. So as soon as there is an alert, we'll policies will be kicked in, and the anomalous workload can be terminated as in then. So it keeps us one step ahead of the attackers. Now let's understand what is defense in-depth strategy. So this is a strategy wherein there is no single point of failure. As we saw in the previous architecture, there are multiple layers. So if one of the layer security is compromised, we are still protected. So this strategy is applied on multiple times. So first is at the build time. At the build time, we ensure that all the images that we are using are scanned and are downloaded from a trusted source or a trusted registry. We validate the SBOM generation. The SBOM stands for software bill of material, where you have a list of all the components with their versions, which increase the transparency in case of vulnerabilities. Similarly, at the deploy time, we have admission controllers, policy enforcement, and identity provisioning by SPIFFE and SPIFFE that we'll cover later in these slides. And also we'll cover how, as moving ahead, so we have runtime security. So in the demo also, I'll demonstrate how we set up Falco to do runtime security and how things take care in the real time. And also, as the fourth point we have, so integration points, basically these are integrated as part of our CI/CD process, and Kubernetes native controls are also taken place. So for example, Kubernetes admission controller, pod security, and other network policies as well. So these are some of the strategies that we follow to make sure that we are defense is till the depth of our application. So enough of theory. These are some of the open source tools that we'll be discussing today. So we have SPIFFE, Spire, Falco, SE Linux, and AppArmor.
So first, we'll look at SPIFFE and Spire. These help us in identity and authentication of the workloads. SPIFFE stands for Secure Production Identity for Framework for Everyone. These are set of open standards which are securely identifying our software in a dynamic environment. SPIFFE provides SPIFFE ID, SV ID, that is a cryptographically verifiable identity which they can verify and test whether the workload is safe for the cluster or not. We have Workload API, which gives the containers these IDs. Trust bundle. If any ID is signed by any key of this bundle, we can define them as safe. We have Spire, which is the runtime environment for SPIFFE. Spire is the one which handles or issues and manages these identities to the clusters. It handles workload attestation. It basically monitors every ID. It checks whether it is valid or not. It continuously checks it and it verifies whether it is the same workload which was tested before. It also supports cross-domain or cross-clusters. Like it will give ID, the SPIFFE ID in one cluster, and it will monitor the other cluster, whether these IDs are changed or not for any anomaly.
Next is the critical layer, that is the access control layer. So for that, we have AppArmor and SE Linux. AppArmor is a Linux kernel security module that provides and prevents unauthorized file access. We can take an example of a simple web app. Web app has only if a web app is configured, it should only have permission to access its logs and the public static files that are stored. So here is a snippet of AppArmor profile snippet where we allow the application to access /user/bin and var/www, and we deny other capabilities like sed UID, or we deny other we deny to access other sensitive files like /etc/shadow, so that our user credentials are not compromised. The other alternative is SE Linux. So it's a bit complex but more granular. So these are extensively adopted by enterprise because it helps them in auditing, and it follows a granular approach by label-based security model. Next up is for the runtime security, as we discussed, we have Falco, and I'll be showing it in the demo. So it is a eBPF-based monitoring, wherein we can go till kernel level and we can monitor system calls, file operations, and network communication. Since it is built on eBPF, so it requires minimal CPU overhead, less than 1% to monitor your environment or your cluster. and it supports real-time behavioral analysis. So these are few of the detection capabilities it have, and it also has a UI, and as I previously mentioned, it also raises the alerts that can be integrated through your ecosystem.
This is a table that we created for simplifying the functionality and key features of these tools. For identity and authentication, we have SPIFFE and SPIRE. The main feature of these tools is to attest the workloads or continuously monitor the workloads. For the function runtime security, we have Falco, whose key feature is using eBPF monitoring. For the function access control, we have the tool AppArmor and SE Linux. And the key feature of it is kernel level policies. For the function policy engine, we have OPA Gatekeeper, and its key feature is admission control. For image security, we have cosign and notary. Its main feature is image signing. Now let's see what is behavioral fingerprinting. It is basically understanding the default nature of container and then comparing it with the difference that it has with the basic behavior of the container. Like suppose a container is used to accessing internal files, but suppose sometimes it tries to access any external file. So this is an anomaly. So this is basically creating a fingerprint of the basic behavior of a container and then comparing it with the change of behavior. This is used for anomaly detection. If any anomaly occurs, it raises an alert so that we can act upon it. We have some practical examples of it. Suppose the web server. Its main function is to serve web pages. And suddenly it starts to scan internal networks. This is an anomaly. Database container making external connections. So database is only the basic feature of database or internal database is trying to access only internal data. And suddenly it tries to access external data. So this is an anomaly. And not only that, suppose we have an upgrade and a container tries to access a new file. So this is not an anomaly. It has to adapt to the new changes, and it should not only search the known vulnerabilities, it should adapt to the new changes. And it should not raise false positives.
Enough of the theory. Let's move to the demo part. Now let's simulate the environment, and we'll act as both attacker as well as we'll set up Falco. Let's move to the demo. So here we have a demo setup, and here I have a Minikube cluster, which is used to set up a single node cluster in my local system. So I have a Minikube cluster here. So I run the command Minikube start to spin up my cluster in my local environment. Then I have to add a Helm repo. So I run a command Helm repo add Falco security. So you can find these in the Falco documentation as well. And apart from that, now once we have added the repo, we'll download the latest Helm chart from the command Helm repo update. It will download the latest chart from the repository that we have added. Now we need to wait for some time. We need to wait for some time to for the pods to spin up. So we'll run the command kubectl get pods. Yeah, so we'll run the command kubectl get pods, and once we have our Helm chart installed, we'll wait for the pods to pod to up and running. Once they are up, our monitoring is set up. We are real-time monitoring the Falco. Now, sorry, our application. So now we'll act as an attacker. So I'll create a symbol Nginx deployment. I have created that, and this is my pod with Nginx that is running. Now I am an attacker, and I try to access some of the sensitive information that is, I've tried to look at /etc/shadow. So these are my credentials or the account with encrypted passwords. So as soon as I do this, I get a warning saying that sensitive file was opened by a non-trusted program. So as you saw that as soon as someone or a non-trusted program tried to attack or open some of the sensitive files, I got the alarm. Similarly, we can also add our custom rules. So this is a custom rule where I have added that no one should be allowed to write in /etc directory. So I have created this custom rule, and we can save this YAML, and then just I need to run the command helm upgrade, followed by the custom rules that we have set up. So you can see the revision 2 is installed, and now we have upgraded our helm deployment, which was there. So again, we need to wait for some time to get the Falco up and running. So once our pod is running, then now again I'll act as a attacker, and I create a simple Nginx deployment that I was having. I'll try to write a file in /etc directory. So as soon as I try to write the file there, I got the warning from Falco that the path was opened for writing a file. So similarly, if attacker tries to attack or try to attack or open some of the sensitive information, similar warnings we'll get. Also, Falco provides out-of-the-box sidekick UI, so that can be also enabled using a flag. So I run the command helm upgrade, followed by the helm chart name, and then we can set the web UI enabled to true. Again, we need to wait for some time to service to come up and pods are in place. Then we can expose the ports, and we can also view the Falco UI. So you saw the previous warning that file was being written on /etc. So we got it in the web UI as well. So this was a quick demo of how a real-time security is detected by Falco in a real-time cluster scenario.
Let's see some real-world attack scenarios. For supply chain attack, we have SolarWinds and Docker Hub. So what attackers do is they insert a malicious code in the software update from organizations' software, and then they pass this update for customers to download it. So this is a supply chain attack. For Docker Hub images, so attackers have simply uploaded many trustworthy looking images which have tampered the open source base images. And the traditional defense mechanism is static scanning, so which will miss all these runtime based attacks. And with zero trust defense mechanism, we have the tool Falco, as you already shown the demo, Akshat. And by Falco, we can detect all these runtime vulnerabilities. We have dirty pipeline vulnerability, where attackers try to escape from container by overriding the normally read-only files from the host. So they use it for getting the access privilege from an unprivileged container. So this mechanism, this vulnerability is not detected from the traditional defense mechanism, which is a perimeter-based security. That means trusting everything that is inside the network. But the attackers have attacked the host file. So using the zero trust defense, we have tools like AppArmor and SE Linux, which blocks even if access is granted, because they continuously check for escalated privileges. We have for cloud lateral movement, pod-to-pod attacks. For example, an attacker has attacked one pod, and then it will try to move to another pod for gaining the credentials and exposing it. So this is a pod-to-pod attack. Using the traditional defense mechanism, which is role-based access control, that is often more permissive. Using the zero trust defense, we have tools like SPIFFE and SPIRE, which will give cryptographic identity for every workload. So it will continuously monitor it and check whether the lateral movement is there or not. And if it is there, it will stop it.
Now let's see some of the success stories by some of the case studies that we have mentioned here. So first is the financial services case study. So from Capital One. So Capital One is a financial services firm, and they need to ensure that a regulatory compliance is protected because they have the trading data and customer data. So they adopted SPIFFE and Falco for their real-time detection. They cut down their security incidents by 90%, and also pass the SOC 2 compliant audits, and that speed up their developer delivery as well. Similarly, we have a healthcare organization called Cerner Corporation, which is a major healthcare IT firm, and they need to meet HIPAA compliance. So to ensure that, they also adopted an policy enforcement and continuous compliance check using Kubernetes admission control and runtime security. This automation hit their 99.9% uptime and improved real-time threat detection as well. Next is the Shopify. Many of you and us are using Shopify under the line on many of the online stores. So during peak sales or Black Friday sales, they spin up 10,000 plus containers, and using these Kubernetes native policy enforcements, they reduce their attacks, and also they achieved 85% of incident response, and also nearly a good uptime during these traffic surges. So that was a great story from Shopify as well.
Let's see some of the key takeaways from this session. So static image scanning isn't enough to protect our containerized workloads. Runtime behavior and strong identity are just as critical. Zero trust means verifying identity and enforcing policies continuously, not just once during deployment. And open source tools like SPIFFE, Spire, SE Linux, AppArmor make these powerful security models accessible and effective today. So thank you for being a patient listener. We are open for any questions that you may have, and these are our socials. You can connect with us. Thank you.
Thanks, everyone. Feel free to connect with us, and we'll take this conversation ahead. If you have any questions, please feel free to ask, and you can connect with us on socials as well. Thank you.
Thank you. Great session. When we talk about security, all of these solutions, identity providers, etc., these are nice, but why not talk about things like micro VMs and others? There's been a lot of work, right? So for Firecracker, they've tried to create a what's the name of? There is a demonized version of it,
Okay.
Docker compatible CLI, etc. So why not look at those solutions which are basically safe by default instead of trying to duct tape a solution around the whole problem?
No, that's a valid question, but here the things are, it depends on the ecosystem what you are using, right? So if you are into Kubernetes and other stuff, then you have things in place. But if I use some of the other services, then these products might be useful at that case. So that's why that's why this was the solution to our problems that we introduced there. So
These are free and open source, so anyone can use it.
No, even Firecracker is open source. So
yeah, that's true. But there are multiple solutions, but we try to cover like most of them what we felt of, which will solve most of the use case of the developers here or Kubernetes administrators. Cool.
Yeah. You mentioned about using SPIFFE, right? I have a follow-up question there. Who is verifying this SPIFFE and like for what purpose?
So SPIFFE has a runtime called Spire, so it manages everything. Like
Okay, but that kind of issues the identity, right?
Yes, basically, so it in a workload, it assigns a cryptographic identity to each of the workload there. So the main purpose of that is so that no malicious workload is injected by any of the attacker, and it basically safeguards us by verifying that cryptographic identity, whether it is coming from a trusted source or not.
Who is doing this verification? Where the verification is happening is the...
In the agent SPIFFE. Oh, sorry, Spire, yeah.
Okay.
Cool. Thanks, everyone. Thanks for being patient listener. I hope you enjoyed the talk. Thank you very much.